Low G Accelerometers, Part 1, Basic Knowledge of Accelerometers. Welcome to the training module on Freescale Low G Accelerometers. The intent of this module is to provide you with an overview of acceleration sensors and basic knowledge in accelerometer technology. MEMS, microelectromechanical systems technology, is inherent in micron-sized mechanical devices that can sense, process, and/or control the surrounding environment. Sensing capabilities derive from mechanical features measured in microns. Freescale's MEMS-based sensors are a class of devices that build very small electrical and mechanical components on a single chip. Here are some of the typical applications for acceleration sensors, which cover a wide range of products in multiple industries. Target markets include consumer, instrumentation, industrial, healthcare, and automotive applications. There are several sensing functions that accelerometers are capable of detecting. These are movement, position, fall, shock, vibration, and tilt. Fall is a sensing function that can be used to identify that a large impact is highly probable, which can be integrated into HDDs. It is also used for fall log and motion control and awareness. Tilt can be applied to an e-compass, inclinometer, gaming devices, text scrolling and user interfacing, image rotating, LCD projection, physical therapy, and camera stability. Movement covers motion control, pedometers, and general movement detection. Positioning applications require more complex algorithms for double integrating the acceleration to determine position. Position applications include personal navigation, car navigation, backup GPS, etc. Shock applications include fall logs, black box event recorders, HDD protection, and shipping and handling monitoring. Vibration applications include high sensitivity and high frequency accelerometers for seismic activity monitors, smart motor maintenance, appliance balance and monitoring, and acoustics. Understanding the range of acceleration for an application enables a product to be designed with the optimal accelerometer. This graph shows applications and their respective acceleration ranges. As you can see, every acceleration range has different applications. For example, fall detection and tilt control is in the 1G to 2G range. Shock detection is in the 2G to 8G range. Vibration is in the 8G to 10G range, and a pedometer is in the 20G to 30G range. Freescale has acceleration sensors with detection ranges from 1.5G to 10G in the low G portfolio of accelerometers, 40G to 100G in the medium G portfolio, and 150G up to 250G in the high G portfolio. Let's take a closer look at the sensing functions that are achievable through using accelerometers. Let's start with the things to consider when measuring freefall. The range will typically be plus or minus 1G. What is the cross-axis acceleration? Is it in freefall and being moved, or is it just in freefall? And also, what is the height requirement for detection? Some people will require a height of 1 meter, while others will require a height of a couple inches. Detection in both instances is achieved by the sampling rate of the microprocessor and how involved the algorithm is with the microcontroller. 3 types of freefall can be determined: linear, rotational, and projectile. With linear, the accelerometer will be dropped in one translation down from the height to the earth. For rotational, the accelerometer will drop, but it will also have a spin to it and a rotation. Third, the projectile fall is when you throw the device, so not only will it have a horizontal movement as well as a vertical movement, but it will also have a slight rotation in it as well. To achieve the highest resolution of tilt, the angles of operation are needed to determine the sensing axis that would be optimal for the application. The second thing to consider is how the accelerometer is mounted. How is the accelerometer going to be mounted on the PCB, and how is the PCB going to be mounted on the equipment? Here shows the typical tilt equation. V out equals the sensitivity of the accelerometer multiplied by 1G times the sine of the tilt angle, all added to the offset voltage of the accelerometer. The accelerometer output will vary from negative 1g to plus 1g when it is tilted from negative 90 degrees to plus 90 degrees. It is important to note that since the output is not linear, the mounting orientation that achieves the most sensitivity is when the sensing axis is parallel to the Earth's surface. Here are some considerations for measuring position and movement. First is the displacement. How far will the accelerometer be moving to detect the change in movement? What is the G range of the device? If it's going to be on a person, the levels are at a higher G-force and require a higher G-range accelerometer. If it's going to be a very small change, such as in a G-mouse, it requires an accelerometer that's even more sensitive. In this case, a lower G-range accelerometer is needed. After this sensing axis has to be determined. Where is it going to be moving? In the X-plane, the Y-plane, or Z-plane, or all three? This answer will determine how many sensing axes are required in the accelerometer. For determining velocity, integration is used. To determine position, a double integration is performed on the acceleration data. The biggest thing to consider for shock measurements is the G range. The accelerometer uses the deceleration of the object being measured to determine the shock. For example, a force of plus or minus 1g is measured for shock detection during tapping, or measured up to plus or minus 250g during a car crash. The algorithm for each design also varies with the type of shock or fall that it's receiving. The algorithm entails setting the threshold at a predetermined shock level. For measuring vibration, the first thing to consider is the frequency of the vibration. This will determine the type of roll-off frequency for the different devices that Freescale offers. The second thing to consider is the G range. Depending on the vibration measured or the strength of the motor, there will be a different type of G range. This means you might have to go with a small plus or minus 2.5 G accelerometer for a pager vibration, all the way up to a 10 G accelerometer for a washing machine out-of-balance detection. The third thing to consider is the accelerometer and where it's mounted. Depending on the mounting, there will be a different acceleration, which also depends on the cross-axis sensitivity of the accelerometer. Freescale accelerometers are two-chip solutions. There is a control IC on one die and a sensing cell, also called the G-cell. The sensing element is sealed hermetically at the wafer level using a bulk micro-machined cap wafer. The G-cell is a mechanical structure formed from semiconductor materials, polysilicon, using semiconductor processes, masking and etching. It can be modeled as a set of beams attached to a movable central mass that move between fixed beams. The movable beams can be deflected from their rest position by subjecting the system to an acceleration. The control IC measures G-cell capacitance and extracts acceleration data, provides amplification, signal conditioning, low-pass filtering, and temperature compensation. Freescale has X-axis, Z-axis, XY-axis, and now XYZ-axis solutions in one package. These sensing axes options fulfill the designer's requirements for single, dual, or triple axis sensing. Note that orientation is not a problem because for each solution, the accelerometer can be mounted flat on the PCB. Freescale's G-Select low G acceleration sensors are designed to detect on 1, 2, or 3 axes, allowing the end application the freedom of movement detection it needs. In addition, for multifunctional applications, these devices allow to select between 1.5 G to 12 G levels of acceleration. The product portfolio includes both analog and digital I2C SPI products. These devices have a fast response time, low current consumption, low voltage operation, and a standby mode all in a small profile package to detect fall, tilt, motion, positioning, shock, or vibration. Freescale's G-Select low G acceleration sensors are designed to detect on 1, 2, or 3 axes, and devices allow you to select between 1.5 G to 12 G levels of acceleration. The product portfolio includes both analog and digital I2C SPI products. The figure here lists all low G acceleration sensors.